Hi everybody. I could sit here and listen to Final Fantasy VI all day because it is... I feel like if there was one game that summarized my entire childhood, it was Final Fantasy VI. It's probably the most important game to me. It's not my favorite game ever, that's Super Metroid. But Final Fantasy VI is probably the most important game, for my, formative years, I guess we'll say. So, and guess what? If you're a Final Fantasy fan, Final Fantasy VI is coming out on the Pixel Remaster version tomorrow. So we know what I'm going to be playing during the break. I might actually be playing it and just have it in the background. I might just pop it up on the screen or something. I don't know. But I'm definitely looking forward to that and hearing all the remixed music because it will be fantastic. But instead, for you guys, I have a different treat, I guess. I don't know, prepared for you. And that's the last real chunk of the class is what we're going to start today. So I kind of like to divide the class into three pieces. The first would be like fundamentals, which would be like the math stuff that we did at the start. And then the second chunk would be the chemistry essentials, which would be like what is an atom, basic bonding, making basic formulas, naming stuff. So we did all that. Now we're going to enter the third part, which is chemical calculations. And so what we're going to be doing here is we're going to be taking all the information that we've learned and then putting it all together in a meaningful way that will help us do analytical work. You're going to use a lot of the stuff that you see in this section of the class, so units 12 through 16, in both Chem 161 and 162. 161, we're going to work more with the stuff that we cover in Unit 16, which is molarity. The stoichiometry and stuff we're going to save more for 162. But in particular, the calculations that we do here are going to be relevant to labs and things. So if you're taking 161 with me, you're definitely going to want to know how to do molarity, which is going to be the last unit of the course. Because we'll talk about it in Chapter 2, I want to say. No, Chapter 6 in Chem 161. And then I, basically throw you into the deep end and, here you go. Here's the lab. Good luck. Because we've already talked about it in 140, right? So if you have questions here, make sure to answer them. Because we're going to need them. We're going to need to know this stuff. Administrivia stuff down at the bottom of the screen. You can see last call for quiz number 5 is tonight. That closes at 11:59. Make sure you get in by the deadline. Quiz number 6 is also due today. So get that one in too. But if you have both quizzes left to do, just do quiz 5 tonight. That's more than enough, right? Do quiz 6 tomorrow. Because it will close tomorrow. It's due tonight, but you have that 24-hour grace period. So. All right, you are going to need this website, which I don't believe we've used yet. That's the wrong website. I want to grab ptable. Well, you know what? Let's give you ptable also. So, if you don't have a periodic table handy, you're going to need a periodic table. So here's ptable. But you're going to need this website as well. So we'll get to what the Lentech website is. I just use Lentech for this purpose. There are probably hundreds of other websites out there, but this is the first one that popped up. And remembering to type Lentech was always, I don't know, it's just some water treatment or whatever company. But they have a molecular weight calculator on there, and that's going to be super relevant to us in just a second. So way back in Unit 7, we were calculating the atomic masses of elements on the periodic table in regards to all the different types of isotopes that were available and their percent abundances and their individual masses, so we could get the average weight of each atom based on all those isotopes. What we're now going to do is we're going to do this for a formula. So instead of just saying, oh, carbon is 12.011 AMU, because that's what ptable says, right? We are instead going to get a formula and just sum everything together. So here's ptable. We'll put that on the screen here. Boop. And if I wanted to figure out what oxygen's molar mass was, well, there it is right there, 15.999. But what if I wanted to do H2O? I would have to take 2 hydrogen, so 2 times this number, plus oxygen, which is 15.999. And I get like 18.02 or something. That's nice and all. We can add numbers together, but you know what's even better? Not having to do that. So here's Lentech. So Lentech has what's known as a molecular weight calculator. And basically, you type in your formula. I already had KCl because I was doing something else in here. And you hit enter, and it says, oh, hydrogen weighs 1.01. Oxygen weighs 16. I'm going to sum all those together, and here's the result. And let me ban this person real quick. This is how much it weighs in AMU. You'll notice that there's another unit up here. We're going to come back to this in a second. But basically, we can use Lentech to calculate the molar mass or formula mass of any stuff that we want to. So that website is now in your toolkit. You type in any formula you want. There are even some known compounds. I don't know if you can actually see that. Is this showing up when I do this? I have to put this over here. Does it show the drop-down window? No, it doesn't. So if you click on this, it shows a bunch of different compounds. So for example, if I wanted, like, say, where's glucose? There's glucose. If I wanted, like, table sugar, then I could get the result there. There you go. Or you can pick any element you want to. I don't even know which one Oh, okay. It's like, wow, that's really large. I don't know which one that is. Yeah, it turns out it's one of the radioactive ones. Okay, so, yeah, that exists. That's a thing that we can do. So, for instance, if I wanted you to tell me what the mass of SNF2 was, or tin 2 fluoride, you could do that by adding these numbers up off the periodic table. And this is the result that I got when I did that. Or, you know, we could just go to Lentech and type it in here. So, doot, boop. And look how close it gets. That's real good. So the point is, I've shown you how to do this. And sure, you can go to the periodic table and pretend like you're shopping off of it. And I'm going to buy a tin and I'm going to buy 2 fluorine. And then add up all the numbers together. Or, you know, just use Lentech, right? Like, work smarter, not harder. This is an online class. If you want to punch it in the calculator, go right ahead. But if you don't care, we have the internet to do it for us, right? All right, so same thing. You could type this into Lentech and get a number. You should get this as your result. But the point is that you can take the mass of not just an atom on the periodic table, but a formula by summing all of those together. And I'm not going to make you do those exercises because that's kind of a waste of your time and mine, right? Like, you can type these into Lentech, like here. We'll go type in AlCl3 and get its mass. There you go. All right. As long as you know how to do it, that's really all I care about. Sorry, I had to move the headset because my ear was itchy. Now I have to readjust it, so there we go. All right, cool. We can do formula masses. That's all set. Here's the part where we're going to want to actually do calculations. So if you know the formula mass of a compound and you know its percent composition, you can learn all sorts of stuff about elements and their constituent molecules that they belong into. This is more or less the very first way for people to determine formulas. So what we're going to be doing in this section, and also the next section, is very elementary. What's the chemical formula of this compound? How do I figure this out? Now, it's not difficult to just kind of obliterate compounds into their constituent elements and then just collect the elements. People have been able to do that for a long time. And then they could collect, like, oh, okay, well, this is what the sample weighed. Here's the mass of the carbon in it. Here's the mass of the oxygen in it. So now I know its percent composition. So percent composition is not super difficult to acquire if you just pump a ton of energy into a compound to break all of its bonds and return all of the stuff to its constituent elements. This is the formula for percent of anything in a compound. So if you know the mass of whatever X is in AMU, and you divide by the formula mass in AMU, and times that by 100%, you can get... Oh, you get real tired, apparently. You can get the percentage of X in that compound. Now, if you have multiple of an atom, then you do need to include all of the parts, or all of the copies of that in here. So include all atoms of X. So for example, if you wanted the percent carbon in C2H4, you would include 2 times the mass of carbon in here. So you do need this 2, because there are 2 carbons. And then the mass of the compound would be the whole thing's mass. And so we'd go to Lentech for that. It'd be something like 28 or whatever. So let's do an example. So I have water. We know what water is. Water is dihydrogen monoxide, or H2O. What's the mass percentage of oxygen in water? So I want you to try and do that calculation. You know what oxygen's mass is, because you can look it up on the periodic table. You know what water's formula mass is, because you can Lentech it, or you can add oxygen to 2 hydrogens. Make sure that you have at least 4 sig figs in your calculation, which Lentech will assure that you do, because it will add the molar mass of hydrogen to oxygen, and you'll get a 4 sig fig number. Go ahead and try this. Tell me what percentage you get. It should be remarkably large. Most of water is oxygen, it turns out. I'm going to give you 3 minutes to try that. Type your answer in the chat, and we'll go over the result in just a bit. All right, 1 more minute. We'll go over the answer here. All right, according to Lentech, the molar mass of water... I'm going to keep calling it molar mass on accident, when I should be saying formula mass. You'll see why it's called molar mass later. The formula mass of water is 18.02. And oxygen would just be the O part of that, or 16.00. So let's go over here. We'll turn this off and go onto this screen. I can capture that a little better. There we go. And let's do that calculation. So the percent by mass of oxygen would be the mass of oxygen divided by the mass of H2O times 100%. So that would be 16 AMU divided by whatever water was, which was 18.02. And you'll notice that these cancel out. And I want to say it's like 80 something. So I think 88 might be right. 16 divided by 18.02. Oh, I got times by 100. There we go. And there you go. So in water, oxygen is 88.79% of the mass of your water, which is a lot. So you're basically drinking almost entirely oxygen. Let me open a can of oxygen here. There we go. It's not really oxygen. There's some hydrogen in there, but my polar seltzer. This one's just original flavor. When you become a late 30s individual, you too will develop a strange and unusual addiction for carbonated water, I guess. I don't know. Is this like a coming of age sort of thing? Like, I'm officially old now? Hey, I like water with bubbles in it. Yeah, that's great. There we go. This is what I got when I rounded on whatever source I used. I don't see how I got 88.80, but whatever. Close enough. All right. On this slide are a bunch of problems, and what I'm going to do is I'm going to go through all of these, because if I give you like 5 minutes to do these examples each, it will take a lot of time. So what I'm going to do is I'm going to let you try and get them started. So like 2 or 3 minutes on each one. And then we'll continue. So you won't have enough time to solve all of these, but like there's a lot of problems that we're going to be doing on this slide. And they're all different applications of this, so they're all going to be kind of a little bit weird. So the first one, I want you to do the same thing you just did, but I want you to determine the mass percentage of aspirin. So here's the formula for aspirin, C9H804. How many decimals in the periodic table are you using? I'm using at least 4, although if you use Lentec, it only provides 3 for hydrogen. It's close enough for our purposes. Honestly, just use Lentec, and it'll be okay. Don't worry too much about decimals on the periodic table. Try and use at least 4 sig figs if you can. I'm going to give you 2 minutes to do this problem. Just do the carbon part, and that'll be good enough. And then we'll do hydrogen and oxygen together. All right. Oops, that didn't quite do anything. Oh, where is it? There we go. All right, so let's do this for carbon, and then I'll quickly do hydrogen and oxygen. And by quickly, I mean like I'm going to cheat, and I'm going to show you what I mean. So the mass percentage of carbon would be the mass of carbon divided by the mass of aspirin, which is C9H8O4, times 100%. I didn't mean to zoom in there. I was trying to stop my timer. The hotkey I used is the same as zoom in, apparently, on Photoshop. All right. Now, I have 9 carbons, so that's going to be 9 times the mass of carbon, which is 12.01 AMU. And then I need aspirin, which I'm just going to type into Lentech, and you can assume that I did this right. I got 180.16 for that. All right, so 12 times 9 is 108. So roughly 108 divided by 180. I'm going to punch in all the numbers, but 59.9966696. It's a lot of 6s and 9s. 996, so I got to round it up. So 60.00%. Where is my cursor? There it is. I went off the tablet, that's why. All right. So that's 60% of my mass. I could replace the carbon part with the oxygen part, so I'm going to do that for one of these real quick. So if I go like this and I just copy and paste this. So copy, paste. And we just go down here. We'll just erase the part that we don't need. I don't know why I'm doing oxygen next, but I guess we're doing oxygen. So there you go. I can do that, and I can punch it in the calculator. And when I do that, I get 35.52. That should be an oxygen. I don't know what happened there. There we go. But, I mean, this is kind of tedious, right? Why is it 60 and not 59.99? Because the number after the 59.99 was a 6, so I rounded that up to 60. This is kind of tedious, so if I go over here to Lentech, where is Lentech? Boop, there we go. You might notice that if I wind down here and then I highlight this, there's a column that already does this for you. So the mass percentage is already being calculated when you go to Lentech and you just type in the formula. So you could type in the formula of anything you want. So I could do glucose, which is C6H12O6. And there you go. Glucose is 40% carbon, 53.28% oxygen, and 6.71% hydrogen. So I can do this for any compound I want. So figuring out the percentages is trivial, and you can use Lentech for that. Would it be wrong on a test? No, I do plus or minus like 3 or 4 in the last digit. So if I expect you to do 4 sig figs, I would accept any answer between 59.97 and 60.04 or so. So you would get credit for it. The reason I do that is I cannot anticipate what sources you are using. But if you are using the correct number of sig figs on your sources that I instruct you to, and reporting your answer to the correct number of sig figs, then you will get an answer that falls within that tolerance, and you'll get credit for it. All right, so that was the first question. Let's go to the second question here. Oh, there is no second question because I had to do this. Doot doot. All right. You could figure out the formula mass easily, you figure out the mass percent if I give you the formula. What if I give you the percent composition and ask you to work backwards? This is significantly harder. And my advice to you to try and do this, I'm going to give you like 3 or 4 minutes to try this real quick, is I'm going to write this down here. I'm going to leave one of these on the screen here, but I'm also going to write this formula. And then my big hint to you is going to be that this right here is equal to this. Okay? That's my hint. I want you to determine, at the very least, how many carbons are in ibuprofen. Now, there's 2 ways to do this. There's the cheating way, which is you type ibuprofen in Wikipedia, and you find out that it has 13. Oops, spoiler. Is it 13? No, I'm thinking of something else. I don't know what it is, but we'll calculate it. Or more appropriately, you'll calculate it. I'm going to give you about 3 or 4 minutes to try and do that, and I hit the wrong button again. So. Oh, I grayscaled everything. No, I hate that. Can I ungrayscale it? What if I hit 2? Oh, that works. Look at that. Okay, cool. All right, go ahead and try this, and we'll be back in like 5 minutes. All right, one more minute, we'll go over the answer. I know I said I wasn't going to go through these super slow, but now I kind of feel like, hey, we need practice. So go ahead and try them. All right. So the way to do this is the following. So in order to figure out how many of each atom are in here, the variable that you want to solve for is actually this right here. So for instance, if I do carbon, I know that carbon is percent carbon equals the mass of carbon, which would be some number times the mass of carbon divided by the mass total times 100%. And if I solve for this variable right here, it turns out I know this. This is 75.69. This is just a number. This is 12.011, and this is also just a number. So I can rearrange this expression in the following way. So I'm going to move this to that side, and I'm going to move this to that side, and I'm going to move this to that side. And doing all this algebra, I would get percent carbon divided by 100% times whatever the total mass was divided by the mass of carbon. That would be how many carbons there are in this sample. So let's fill all that in. So I had 75.69% divided by 100%. My percentages cancel. Times the total mass of ibuprofen, which I gave you, divided by the mass of one carbon. I have an extra 1 in there. That's fine. Doesn't really matter. And when I do this, I should get an integer. And that integer should be the number of things that are in there. So 75.69 times 206.29 divided by 100 times 12.011. And I got 12.9998, which we're going to round up to 13. And it was 13. Now look at that. Now you could do the same thing with all the other elements, and we'll do that really quickly. So we'll just copy and paste the formula. Percent H over 100% would be the total mass divided by the mass of a single hydrogen. And that would be 8.790% over 100%. Do I listen to chemistry on the way to work? No, this is my work. I walk 5 feet from my bed to the computer. I don't have to listen to chemistry. I don't have any time. It's just right there. I do occasionally read articles about chemistry. Honestly, though, like the majority of my my time when it comes to like, hey, what do you listen to for fun or whatever, is virtually anything else besides chemistry. Because 2 reasons. One, I'm an expert already in chemistry. Like literally, I've studied this for 12 years of my life. So what did I get? 17.9889. So that's going to be 18. I've studied it so much that I know virtually like 95% of the chemistry that's out there. Like, there's new stuff, of course, and that's always exciting and fun. But I don't seek that out. So, like, physics is more interesting to me, for example, because I know a lot less about physics. And then I have to do, like, the whole Wikipedia rabbit hole thing, where it's like, oh, I get to go learn about quarks again. Because I swear, every time I read about quarks, I'm like, I wish I knew more about this. All right, so this one will be 15.51 over 100. And those cancel. I didn't cancel these out up here. Times the total mass over a single oxygen. And what are we going to get? We're going to get 2 for this, or 3? What did everybody else get? They got 2. 206.29 over 100 times 16. 1.99997. So cool. So we would then take these numbers. And there you go. That's your formula for your stuff. And it's really cool that we can do that. Because figuring out formulas is very difficult to do if you have like limited technological accessibility, I would say. So like a long time ago, like late 1800s, early 1900s, maybe even early 1800s. I'm not so sure on the time frame here, but the point is that we could do this type of thing with very limited technology. Because mass percentage is pretty trivial to get. The hard part of this would be figuring out the molar mass. But there are ways to do that. All right. The next question that I have for you is this one. What is the mass of hydrogen present in 20 grams of acetone? This should be pretty trivial to do. In fact, you probably do this in like 20 seconds if you look it up on Lentech. So I'm going to give you more than that. I'm going to give you 2 or 3 minutes. We'll go over the answer then. But type your answer in the chat if you got one. All right, one more minute. We'll go over the answer here. All right, let's give this a shot. So, more or less the same strategy here that we've been applying. So let me clear all of this. Oh, right, I have multiple layers now, so I have to delete this layer. So now I can do that, because I copied and pasted something. Okay, so if I know what the percentage of hydrogen is, then I would be able to multiply by my sample to figure that out, right? So we could say how many hydrogens are in acetone. So it looks like there are 3 per CH3, and there are 2 of those groups. So 6 times. So there's hydrogen. And then the total mass, we'll just lentech that, because it's probably like 60 or something. CH3 parentheses 2 CO. 58.08 is what I got. And when I do that calculation, looks like I'm going to get something like 10. 10.41, yeah. So acetone is 10.41% hydrogen by mass. Now, what this also means is that I could write this as the following. These are the same thing, right? There are 10.41 grams of hydrogen per 100 grams of acetone. That's a true statement, because that's what this means if this is by mass, right? In fact, if I put these numbers into the equation, I get the same thing out, yeah? I could also have written this, but this is more intuitive once we have the percentage. So now what I can do is I can say, well, I have 20 grams of acetone. And you might have just said, well, I'm just going to multiply this by that and get the answer, right? And you totally can do that. It's just that I'm going to do this in a different way. I'm going to do it this way just to show you where the units go. So if you intuitively just said, oh, I'm going to just take that percentage, make it a decimal, and times it by 20, that's the right answer. But this is where the dimensional analysis is going. So now I just take 20 times my answer. And I get 2.08 grams of hydrogen. So in a 20-gram sample of acetone, 2.08 of those grams are hydrogen. I only get 3 sig figs because I only have 3 sig figs here, for what it's worth. All right. I do have one more problem for you. And I'm going to just put it on the screen real quick. Because we're at our break. We're going to take our break now. But when we come back, we're going to do this problem. A molecule with only one carbon atom is 74.8% carbon by mass. What is the mass of the entire molecule? And you're probably looking at all the formulas we've written on the screen here and should have some idea of how to solve this. And so if I know the mass of... Actually, let's just rewrite the formula down here. Oh no, what have I done? I've done terrible things to my display. There we go. Oops, sorry. Percent carbon equals mass carbon. Let me just get rid of that. Percent carbon equals mass of carbon, mass total. That's 100%. And what variable are we solving for? We're going to solve for this one this time. So you can go ahead and try this if you'd like over the break. But if you'd rather just take a break, you know, that's what it's for, right? So we're going to put the music back on for Final Fantasy VI. And we'll see you in 10 minutes. Alright, we're back. We'll wind this away. Here we go. I could listen to Final Fantasy VI soundtrack forever. Alright, I'm going to give you 2 or 3 more minutes to work on this problem, just in case you actually took a break. So go ahead and do that, and we'll go over the answer in just a little bit. Alright, 1 more minute. We'll go over the answer. Alright, let's go over the answer here. So there's my formula on the screen here. We're going to solve for the mass total, which means that I just have to switch these 2 variables around, really. So there we go. So what is the mass of carbon? Well, it says in the problem statement that I have 1 carbon atom, and each carbon atom would weigh that. times 100% divided by the percentage of carbon, which is 74.8%. So my units cancel out. And I get 12.01 times 100 divided by 74.8. And so that would be the mass of the molecule. Now, if I asked you, what is the likely molecule, you could say, well, carbon is 12 of that, so that leaves me 4 AMU left. And there's really only one thing I could... Well, there's two possibilities. So there's a carbon-helium compound, or CH4. There are no helium compounds. Helium's a noble gas. So this is definitely what this must be. So you could see that by predicting what the percentages are, and knowing how many atoms there are, you could make a formula out of this. And then possibly predict what the formula is based on the information that you have. So, really, really powerful stuff that we can do with just the mass percentage formula, which is why we spent so long on this. So, in the interest of time, I'm going to leave these 3 problems for you to just do on your own. Number 1, you can literally do on Lentech. Number 2 should match up with what you know about sodium consumption, i.e. you should get like 2,300 milligrams or whatever. And then the third one, you're going to do it just like the problem that we just did, so it should be pretty trivial to do. Just note that there are 2 nitrogens in this one, so... Oops. I don't know why that happened. So that will change your answer very slightly. But we're going to move on to the next section here. Oh, this slide is just telling you how many sig figs should you worry about with formula masses. Honestly, the best answer I can give you is use Lentech. And you'll have at least 4 sig figs. What you want to do is you want to have enough sig figs in your result when you calculate formula mass that it's not going to affect the precision of your answer. In other words, if I give you a number that has 3 sig figs in it, and then I say you have to multiply it by the molar mass or the formula mass or whatever, and you calculate the formula mass to 4 sig figs, it won't affect the precision of your result because you're going to round it to 3 sig figs based on the number you started with, right? In some cases, if you're working with, like, say, H2 or whatever, if you have a very light element and its mass is less than 10 AMU, grab 3 decimal places from maybe, say, P table. So, for example, H, Lentech will just write 1.01. You may want to get 4 sig figs, depending on what you're doing. So, just be mindful of that Lentech is not going to be perfect for very small things, but for large stuff, you're going to get enough sig figs that it will be fine. Alright, so in general, I know that we've been very strict on sig figs in this class, but for formula masses, since you're going to be doing this so often, you could basically trust Lentech, unless it only gives you 3 sig figs. Then you got to do it manually, go get a periodic table that has more digits, and get more sig figs. That's really the only case that you have to worry about. Alright, let's move on. Let's go on to the next thing, which is this new concept that I think we very, very briefly mentioned at the very start of the quarter. We were talking about SI units, and we said there was like length and time and mass, and one of them was temperature, and then the other one was number. And we talked about mole, and then we said we're going to talk about that way later. Well, here we are. We're finally here. So this is a unit of counting. And what we're going to use it to do is count particles. By particles, what I mean are atoms, molecules, formula units, whatever you want. Particles is sort of my catch-all. So this is just going to be any of these things. Sorry, the pen is not great on PowerPoint. Now, it turns out atoms and molecules are very, 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 very tiny. And we have to end up using ginormous exponents to deal with this. For instance, In a 12-gram sample of carbon, there are approximately 6.022 times 10 to the 23rd atoms. And this quantity is what we're going to call a mole. And we're going to define it like this. If you have 1 mole of objects, you have 6.022 times 10 to the 23 of that object, which is an insane number that is very, very difficult to conceive. We're going to try to approximate that in a second here, but first I'm going to give you the official name of it. So, a scientist named Avogadro is the one who pioneered work in calculating this number, as well as various other properties of like gases and stuff like that. And so this number, Avogadro's number, we're going to be using it a lot. And it's so unique that you have probably already memorized it. You don't have to memorize it, but we're going to use it a lot. So may as well have it handy. All right. How big is this number? If I was to write it out, it would look like this. Like, that's absurd. Like, I don't know about you, but my brain shuts down at about this spot, going from right to left. Like, it's hard for me to think of things that are larger than 1,000,000 or 1,000,000,000. Like, what does that even mean? There are 8 billion people on Earth or so, or whatever. Like, what does that even mean? It's just too big at that point. And this is like 15 more digits after that. So I found some examples that I thought would be kind of funny. Let's suppose that you take your workbook. If you bought the workbook from the store, pretend that you had 2 of them and you could stack them end to end so that they were like this. So here's one, and you're going to stack another on top of it. And then let's say that you bought a mole of these. And you just kind of stacked them up higher and higher and higher and higher and higher until you had 6.022 times 10 to the 23 of those placed end to end. How far would your tower reach? Would it reach to the edge of the atmosphere? Would it reach to the moon or the sun? Turns out it would go all the way out of the Milky Way galaxy, and it would reach the next one over, the Andromeda galaxy, and go through it too. That's how far away the Andromeda galaxy is. You need 10 to the 23 textbooks to get there. But then you'd have a nice little bridge that you could walk along to the Andromeda galaxy. That'd be fun. How about money? What if I gave you a mole of dollars? If I gave you a mole of dollars and you decided to be charitable and give it away to everybody else, you would have so much money that you could give every single person on the planet $3 million per second, every second for the next 100 years. And you'd still have enough to live comfortably on. You would out Bezos, Jeff Bezos, by like 10 to 12 orders of magnitude, which is absurd to think about. You would need to have trillions of Jeff Bezoses to get a mole of money. Trillions. One of them has more wealth than anyone else on the planet. You'd need trillions of him to get this much money. And then Toothpaste for Dinner is a really silly comic that I just put this in here for. So, all right. Now, with a mole, we can do calculations of this nature. So what we can do is we can say, if I know how many moles something is, I can figure out how many atoms it is. So I could say, okay, if I have this many moles of carbon, yeah, out Bezos the Jeff. That's the proper way to think of this, right? We can relate these 2 units together, moles and atoms, because in a mole, there are Avogadro's number of atoms. And so we can calculate to 3 sig figs how many atoms are in this sample. And I got still a boatload of carbon atoms. Several billion boatloads, actually. So very simple calculations that we can do, just like we did in Unit 3, where you like turn feet into miles or whatever. Now we're just turning atoms, number of atoms into moles, or moles into atoms. Let's suppose you, the airbag in an automobile is activated as part of a test, and the number of molecules is counted with a sensor, and the sensor detects there must be this many molecules in here based on the pressure and volume of the bag, or whatever. How many moles of nitrogen are in this bag? Go ahead and try this calculation. I'll give you 2 minutes to do it, and we'll go over the answer in just a bit. All right, let's go over the solution here. All right, if I want to turn this into moles, first I'd have to cancel out molecules of N2 and turn that into moles. And in a mole, there are Avogadro's number. Now, if you do this calculation and you get an answer that's like 10 to the 46, what happened there was that you didn't use parentheses around the number at the bottom. So when you're dividing and you have exponents, put a parenthesis around that number, and you'll get the correct answer. And there you go. Now, it's also very difficult to conceptualize these numbers. Like, how much N2 is this? In 162, I believe, we're going to learn that a mole of a gas is about 22 liters or so. So this would be like 50 liters of gas. Now, your airbag's not 50 liters, obviously, but all of the adjoining stuff, like the steering column itself and the inside little chamber where your stuff, adding all of that together, you could get a volume approximately 50 liters. I did also make up this problem, so I have no idea if this is an appropriate number. All right. Here's 2 more problems. I'll have you do them. So I have this many moles of lead. How many atoms is that? And then I have this tiny, tiny gold nanoparticle. Here's how many moles I have, which is a very small number. How many atoms are in a nanoparticle? So those are basically the same problem, so do one of them in the next 3 or 4 minutes, and we'll go over the answer to both. All right, one more minute. We'll go over the answers. All right. Oops. Got nothing on the screen there. All right, so let's clear all that out. And where's my pen? There's my pen. Okay, so I have this many moles of lead. And we'll turn moles of lead into atoms of lead. And we know that in 1 mole, there are Avogadro's number of anything. So that means that there must be 5.03 times 10 to the 23 atoms of lead. And then same thing here. We're just dealing with a really small number. Same exact problem. So moles of gold, atoms of gold. So 5 point... The real trick for this one is making sure that you're typing in your exponents correctly. Oops, I didn't mean to hit divide. 6.022 E23. And I get 3.22 times 10 to the 13 atoms of gold. Which is still a lot of atoms. That is 32 trillion atoms in a nanoparticle. So, tiny, tiny, tiny particles still have large numbers of atoms. Like, very, 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 very large. All right. Any questions on how to do those calculations? Let me know. Because this is going to become a staple calculation. It's turning moles into atoms. We're also going to be turning moles into something else. And that's where this next section comes in. So there's a reason I've been calling it molar mass on accident all period, as opposed to formula mass. And that is because the unit of AMU is designed in such a way that it is also the number of grams in 1 mole of that element. So if you look on the periodic table, for any element, the number that is written as its atomic mass is also its mass in grams per mole. So I have 2 examples here. These are carbon and iron that I've just taken straight off the periodic table. And so each element has a molar mass, and it's on the periodic table. What that means is that each molecule composed of elements on the periodic table also has a molar mass of its own. And you do it the same way, you just go to Lentech and type it in, right? And so all of the stuff that we've talked about today sort of unifies here. And now we have more different calculations that we can do. What is the molar mass of xenon? You can look it up on the periodic table. You can look that up for uranium. Also, xenon is like, I don't know, where's my periodic table? It's buried under a bunch of stuff. Where is my periodic table? There it is. It is under a bunch of pads of paper and Volo's Guide to Monsters and Xanathar's Guide to Everything because I was looking at D&D stuff earlier. What is xenon? Xenon's 131.29 and uranium is 238.03. Those are just on the periodic table. And those are in grams per mole. And then same thing for compounds. And for any compound, you could type this in. We're just speeding through this because it's trivial, basically. So if I wanted the molar mass of PtCl2, for example, we could go right over here to Lentech, which is still captured, so we'll just do this. You just type it in. So there you go. So 1 mole of platinum 2 chloride would weigh 265.98 grams per mole. And those units are given on this page right here. So that's where this is coming from. So this is the number of grams per 1 mole of that substance. All right. I'm not going to have you do this example because it would just literally be you typing things into Lentech. So I'm going to assume that you can do that. That compound listed for the third one, yes, I did synthesize something very similar to that. The one that I synthesized would be very difficult to typeset because it's got, instead of H's on that C5 whatever, it's got methyls, so I didn't want to bother with that. All right, so you could figure out molar masses. Nothing really exciting there. Let's go do probably the last thing that we're going to do today. So if I can convert things from particles to moles and grams to moles, and I'm drawing these on a little like chart for a reason, because this is going to be our little blueprint that we're going to follow. I can therefore turn something from grams to moles to particles if I wanted to. In fact, the central place is going to be moles for all of this, because moles are the way that we relate a counted unit to a mass unit. As such, if you're ever in doubt for these types of problems, like what's my first move? What do I do to solve this problem? Try turning whatever it is you're given into moles. See if that helps you, because the number of connections that come off of moles are varied and large, and there's a lot of them. There's all sorts of different things you can do with moles. So let's do some examples of this. I don't need to say anything on that slide, so here we go. Which of these is a bigger mass? I just have quantities of moles here. So let's turn these into grams and see which one has a bigger mass. So let's do that. So 2 moles of oxygen and 16 moles hydrogen. So let's start with oxygen first. How many grams are in a mole of oxygen? Well, if we go to P table, and when I do that, and I click on oxygen, it says down here 15.999. So we'll do that. We'll write that down. So there are 15.999 grams of oxygen per mole. And so when I multiply that together, I get, oh, with 3 sig figs, it's just 32. So a 2 mole sample of oxygen weighs 32 grams. What about a 16 mole sample of hydrogen? That's so many moles. That's got to weigh a ton, right? I was going to write O for some reason. Well, according to P table, hydrogen weighs per mole 1.008. So we'll write that down too. When I do that calculation, I get 16.1. So despite having 8 times as many particles, so there are 8 times as many hydrogen atoms as there are oxygen here, because each oxygen atom weighs so much more than a hydrogen atom does, the total mass of oxygen is greater. So this one has a greater mass. Where'd my cursor go? There it is. All right, now I want you to try it. I'm going to erase that off the slide there. I'm going to give you 34.9 grams of iodine. Just regular old I by itself. How many moles are in that sample? Go ahead and try this. We'll go over the calculation together in a second. One more minute, we'll go over the answer. All right, so let's look at... Oops, hold on. I'm playing around with the periodic table here. So let's look at iodine here. So according to this, here's my iodine down here. 1 mole is 126.90 grams. So, if I have... Oops, I gotta click over here again. If I have this many grams of iodine... I know that in 1 mole there are 126.90 grams of iodine, because that's what p-table told us, right? Again, here it is. And then I can punch that into the calculator. What do I get? 0.275 moles of iodine. All right, so everybody had the right answer, but they had the wrong number of sig figs. Gotta have 3 because my number I gave you had at least 3. And all the other numbers we used had more than that. All right, and that's how we do these types of calculations. Here's one more. I'm going to give you this mass of sulfur, but instead of moles, I want you to tell me how many atoms there are in the sample. So first you'll have to turn it into moles, and then you could turn it into atoms. So this one will take 2 steps, but not twice as long to do. So again, 3 more minutes and we'll go over the answers. One more minute, we'll go over the answers. All right, so we'll do this. There we go. All right, so I have 19.7 grams of sulfur. And what we're going to do first is, so I'm going to start writing out a blueprint here because this is multiple steps. So we're going to turn grams of sulfur into moles of sulfur. And then we'll turn that into atoms of sulfur. How many grams are in a mole of sulfur? Well, according to the periodic table, for sulfur I have 32.06. So you should be able to find that on P table. So if I hit enter here, this would give me the number of moles of sulfur, but I don't want the number of moles of sulfur. I want the number of grams of sulfur. Or I'm sorry, not the number of grams. I want the number of atoms of sulfur. So we'll turn moles of sulfur into atoms of sulfur. And how many atoms are in a mole? Avogadro's number of them. So we'll punch that in the calculator. Divided by 32.06. And I get 3.70 times 10 to the 23 atoms of sulfur. You're going to see that exponent a lot, 23, whenever we're dealing with atoms. A reasonable amount of matter will give you a times 10 to the 23 number of atoms. So, like, on the order of, like, 10 to 100 or so grams or whatever. If you have less than that, you'll get a smaller exponent. Not too much smaller, so like 22, 21, that sort of thing. And if you have a larger amount of matter, you get 24, 25, or so on. And as you do more of these problems, you'll start to get this sort of connection with what the exponent means and then the mass or size of stuff. So like 19 grams of sulfur, not very much. Like you could put that in a little dish, right? Or a little bowl or something. And that would be times 10 to the 23 atoms. So you will eventually develop this sort of intuition that will help guide you to look at a number and say, okay, that number makes sense to me. Like I'm looking at this and seeing times 10 to the 23 and I say, that number makes sense to me. It's difficult to develop that confidence at first because you don't really have a reference, but you will over time. All right, I do have some extra problems for you to try. What I'm going to do is I'm going to leave these on the screen for a few seconds here. You could pause the video and then do these if you'd like. We're going to start here tomorrow. Because I would like for you to have time to work on them before I just give you the answers. So we're going to stop at this point, and then we'll go back over here because we're all done for today. Let's see here. So we're going to finish Unit 12 tomorrow. We're almost done with it. Unit 12 has its own quiz, so that quiz will go up on Wednesday. And then you have other quizzes that you're responsible for tonight. Quiz number 5, which is Units 9 and 10, closes tonight. Be sure to get that in by the deadline. Quiz number 6 is due tonight. It will close tomorrow. Make sure to get that in by that deadline as well. And then tomorrow we're going to talk about lab number 4. And I honestly don't remember what lab number 4 is about. I want to say that it's molar ratios, which is what we're doing right now, and also Unit 13. But I'll look at that and I'll have that ready for tomorrow. That's all I got. Have a wonderful rest of your day. Work on those problems, get those quizzes in, and I'll see you tomorrow. Take care.